Hi everyone and welcome back. So today we're going to be trying to solve initial value problems using Laplace transforms. This is kind of what everything's been building up to with the development of Laplace transform methods. We've figured out a way to transform a function in terms of t, time, into a Laplace transform, and then we've also figured out a way that we can go backwards from the Laplace domain to the original time domain, and we're going to see how we can apply that in the case of linear differential equations and trying to solve their initial value problems. So we're going to get straight into that. Here is our differential equation. We're looking at y double prime plus 4y prime minus 5y equals 6e to the t, with the initial conditions y of 0 equals 3 and y prime of 0 equals 28. So this is our problem. We have these initial conditions. All of this is going to get put together in the Laplace transform world. To do that, we have to recall some rules that we have seen before. And so I just want to quickly recap what those are. So the first is that if we are taking the Laplace transform of a function, and it's of the derivative of a function. So if we want to take the Laplace transform of f prime of t, then what we have seen is that that will be equal to s times the Laplace transform of f minus f of 0. And we've also seen the second order version of this. If we want to take the Laplace transform of f double prime of t, then we get s squared f of s minus s f of 0 minus f prime of 0. And it continues in the same vein for higher orders, but these are the only two that we're going to need for this particular problem. So the idea here is that we are going to start with our differential equation that we saw here, and we're just going to apply the Laplace transform to both sides of the equation. So we get the Laplace transform of y prime prime plus 4y prime minus 5y is equal to the Laplace transform of 6e to the t. So thanks to the linearity of this equation and the linearity of the Laplace operator, we can break up the left-hand side to get the Laplace transform of y double prime plus 4 times the Laplace transform of y prime minus 5 times the Laplace transform of y. And that will be equal to the Laplace transform of 6e to the t, which we should know by now is 6 over s minus 1. All right, so now to apply the formulas that I've just mentioned to y prime prime and y prime. So we're going to call the Laplace transform of y capital Y of s. And so what we get here is that s squared times capital Y of s minus s y of 0 minus y prime of 0 plus 4 times s y of s minus y of 0 minus 5 y of s is equal to 6 over s minus 1. All right, so now we're going to just, what we want to do is, this is change the derivatives into algebraic operations, multiplying by s. And it means that y appears in several places here, capital Y appears in several places, but never with a derivative. So we can just gather those capital Y's together and solve for y of s. So first of all, we gather terms. We get s squared plus 4s minus 5 times capital Y of s. And then what do we have left over? We have minus s times 3 minus 28 minus 4 times 3. And that's it. And that equals 6 over s minus 1. So where did all of these things come from? So we have the capital Y's here, here, and here become that term. And then we have sy of 0 here, y prime of 0 here, and 4 times y of 0 here. Okay, so that's great. Now what we're going to do next is move this over to the right-hand side of the equation and try to continue on from there. So that'll be on our next slide. So let's see. What we have is, we have s squared plus 4s minus 5 times y is equal to 6 over s minus 1 plus 3s plus 40. And before I divide through by the things that are multiplying y, I'd like to get the things on the right-hand side to have a common denominator. So I have 6 plus 3s plus 40 times s minus 1 over s minus 1. And then multiplying that out, I get 3s squared plus 40 minus 3, so plus 37s. And then we have minus 40 plus 6, so minus 34. All right, and all of that is over s minus 1. All right, now I'm going to divide through by this left-hand side. Now you might notice that this is exactly equal to the characteristic, got spelled correctly, characteristic polynomial. That's no accident. In fact, the stuff that's multiplying capital Y will always be essentially the characteristic equation, the characteristic polynomial for the original linear equation that we started with. All right, so we do this, we get that y of s is equal to 3s squared plus 37s minus 34 over s minus 1. And then the thing we're dividing by, we can also factor, it's s minus 1, s plus 5. Now, so here we've arrived at a formula, y of s is equal to this thing on the right-hand side. And so if we knew what the Laplace transform was of this thing, then we would know what y of t is. In other words, we would know the solution of the differential equation. So this is our question. What function y of t has this Laplace transform? It's the inverse Laplace transform question. To do that, we need to appeal to some techniques. So this denominator here is s minus 1 squared times s plus 5. So we're going to try to simplify the right-hand side here using the method of partial fractions. We can rewrite this. Since this is a double linear term here, s minus 1, we need an a over s minus 1 squared plus a b over s minus 1 plus a c over s plus 5. All right, and we're going to put that together and try to figure out what a, b, and c are, and then hopefully these things we will have an easier time finding the inverse Laplace transforms than this huge thing that we started with. All right, so let's go with that. We have 3s squared plus 37s minus 34 over s plus 1 squared s minus 1 squared and s plus 5 equals a over s minus 1 squared plus b over s minus 1 plus c over s plus 5. If you're unsure why the right-hand side looks like this, it would be a good idea to review partial fraction decomposition, which we cover in another video and is also the subject of section 5.3 of the textbook. So you want to have a look at that. All right, so we're going to get a common denominator on the right-hand side. That will give us a times s plus 5 plus b times s minus 1, s plus 5, and c times s minus 1 squared. And that's all over s minus 1 squared times s plus 5. All right, so that's a lot going on. We have the same denominator on both sides, so in order for these functions to be equal, the tops have to match. So 3s squared plus 37s minus 34 is equal to a times s plus 5 plus b times s minus 1 s plus 5 plus c times s minus 1 squared. And we have a couple of techniques for figuring out now what a, b, and c are. We can do convenient values, or we can do comparing the coefficients of s squared, s, and the constants on both sides of the equation. Choose yours. what I'd like you to do right now is take the time to actually figure this out. So I'd like you to pause the video right now and try to figure out what A, B, and C are. Come back after you've done that, continue the video, and we'll see if your answers agree with the ones that I've got. So I'll give you a little bit of time for that now. All right, so hopefully you've done that, and you have yourself some coefficients A, B, and C, and we're going to see if we came up with the same things. I'm choosing to use the method of the convenient values. So I'm going to plug in s equals 1 and s equals -5, because those are the ones that are going to cause things on the right-hand side to go away. So let's start with letting s equal 1. If we plug in s equals 1, we get on the left-hand side 3 plus 37 minus 34. And on the right-hand side, we get 6a plus 0 plus 0. So 6a is equal to 6, so a is equal to 1. All right, we've started out well. All right, let's try another one. Now let's try to let s equal -5. On the left-hand side, we get 75 minus 185 minus 34 equals 0 plus 0 plus 36c. Now if we work out what we have on the left-hand side here, that comes out to be minus 144 equals 36c. And so we get c is equal to -4. Is that right? Hope it's right. Let's think about that. C equals -4. Yeah, looks good. All right, and then lastly, we have to figure out the value of b. There's no convenient value that works absolutely perfectly for this one. So we can just pick another value. I think 0 is easy thing to plug in. So I'm going to say let not b, but let s equals 0. And when I do that, I get -34 equals 5a minus 5b plus c. And I know that a is equal to 1 and c is equal to -4. So -34 equals 5 minus 5b minus 4. And so minus 5b is equal to, let's see, minus 35, and b equals 7. All right, so I've got my 3 values that I need here in order to continue. All right, so having done that, hopefully that agrees with what you got. Having done that, we will continue our problem here. We now know, going back, we have y of s is equal to 1 over s minus 1 quantity squared plus 7 over s minus 1 minus 4 over s plus 5. And so y of t will be equal to the inverse Laplace transform of these things. And so s minus 1 squared plus 7 inverse Laplace transform of 1 over s minus 1 minus 4 inverse Laplace transform of 1 over s plus 5. So a few of these are pretty easy to get. We have 7, and that's going to be e to the t. That one should be familiar by now. And minus 4, e to the 5t. The minus 5t, excuse me. And then lastly, we have to deal with this 1 over s minus 1 squared. And for that, we have to think about our, well, there's a couple of ways to think about it. What I would think is the easiest one is to recall that the Laplace transform of t is equal to 1 over s squared, right? So, following the general formula that the Laplace transform of t to the n is equal to n factorial over s to the n plus 1. So this is that applied with 1 for n. And what we have here is a shifted version of that. So we have it shifted by 1 unit. And what that does in the original function, if the Laplace transform is shifted by 1 unit, is we multiply by e to the t, e to the 1t. So if we come back up here to put all of that into action, what we should have is t and then multiplied by e to the t. So we're going to get t e to the t. All right, and there's our solution. We get that y of t equals t e to the t plus 7e to the t minus 4e to the minus t. And what you'll notice here is that this looks exactly like you would expect it to. There's our complementary solution, c1e to the t plus c2e to the minus 5t, because those are the two eigenvalues. Because the non-homogeneous part was e to the t, we would know that we have to have something of the form t times e to the t. One of the nice things about the Laplace approach, however, is that it takes care of finding the constants c1 and c2 and the unknown coefficient a all at the same time. Right? It just pops out the final answer, the final unique solution in one fell swoop. And that's our answer. So this is how we apply Laplace transforms to initial value problems of differential equations and get ourselves a result. We have solved this differential equation without integrating anything. All of the integration stuff that we might have to do is built in to the Laplace transform process.